Hi everyone, my name is Jakub. I work for the company called Vortexa, and we use machine learning to provide all traders with a real-time view of supply of energy in the oil markets. Which is pretty cool and quite a difficult problem to crack. A lot of analytics, a lot of mapping, a lot of scalable AI buzzwords as well. You can find me on the internet under those handles. And I want to talk to you today about various type systems, specifically 3 of them. One of them is Java, one of them is TypeScript, and one of them is OCaml. A little bit of a disclaimer, I'm by no means a type systems expert. I just happen to be working with all 3 of them, gained some insights into how they work, and kind of formed opinions on how they help me in various different situations. So without further ado, let's get into it. Let's start with Java. I'm going to be specifically talking about Java 10 because it's a massive improvement over your regular uber verbose Java that you're used to. This is a quote that I would like to suggest that it's really because Java would be a very dangerous choice to use in such context. And it's not a bad thing. To me, this is a theme of this compiler: honesty, like flat out honesty. So let's learn about a few features of the type system. So out of the box, you get 2 different types of types. So unboxed and boxed. Unboxed types are something that you would be familiar from background like C or C++. They're just primitives, pure values. No methods, just assign a value, and then you cannot do anything with that value unless you use some utility methods, etc. And they follow structural equality as well. So, literally, if one value is set to one value and another value is set to the same value, they're equal. Pretty boring. There are also box types, which for JavaScript folks you're going to be kind of familiar with, where everything is an object. So you can, call methods on it like toString. And they mostly behave like object/reference types when it comes to equality. Namely, they can hold the same value, but they're generally going to be different because the references are different. And I'm saying mostly because JVM optimizes some of those crazy cases and common cases into singletons, similarly to Python. But that whole thing is for another talk, I guess. So where those 2 types differ the most is when it comes to representing the concept of no value, namely null. And this is a quote from an inventor of null, actually. The most important takeaway here is that null doesn't have any type. Therefore, it means it can be assigned to any box type. And compiler doesn't give you any guarantees whatsoever, doesn't even attempt to do anything about it. And it's clear, it's obvious, you are on your own. So you have to be careful how you code. And again, it's quite honest. It's not attempting to do anything about it. It's just flat out honest that I'm just going to leave you to it. Another interesting feature, should I call it, or behavior, is a type erasure. So Java has good generics like a lot of other programming languages out there. But strangely enough, also Java needs the type information at runtime. So for example, to be able to choose the correct method overloads, etc., etc. The type erasure feature means that all the generics are gone at runtime. So if you've got a list of string and if you've got a list of long, they all look exactly the same to each other at runtime. And again, with the theme of honesty, here's a reasonably simple example, which won't compile, even though to a person who's not worked with Java, these look like perfectly fine overloads. One is taking a list of integers and one is taking a list of longs. But because of this type erasure feature, should I call it, compiler is just telling you, I can't do anything about it. I'm too primitive, but I'm going to be honest about it. Java 10 introduced something that has improved, in my opinion, the type system dramatically, namely local type inference. namely something that a programmer in any other language is kind of used to, where you can type in a var keyword and it's going to figure out what type is that local variable of. This is, by the way, applying to only local variables. It won't infer your method arguments, etc., etc. So you type var and you assign a string value to it, and it's going to figure out it's a string. Great, like any other type language. At the same time, this feature being new is quite it's in quite early stages. So, for example, if you were to assign a lambda to it, which has been introduced in Java 10, it's going to blow up. It's not going to blow up with any cryptic expression. It's just going to, again, very honestly tell you, hey, listen, I can't do it. You have to give me some hints. And I quite like this honesty. I quite like Java, to be honest. So that's my conclusion on Java. It's a very likable friend, not the sharpest, but self-aware and honest about it. Okay, let's catch up with TypeScript, which immediately strikes you as a language with many more advanced type features that I'm gonna try to walk you through in here. And it's even more remarkable. I want to, give credit to TypeScript because it's, in my opinion, trying to achieve the impossible. It's trying to type JavaScript without changing the semantics of JavaScript, and JavaScript is the wildest of the West. Really, so many different ways of screwing things up, and trying to type it, in my personal opinion, is an impossible task. One of those more advanced features are strict null checks, or in general, just TypeScript in strict mode. It promises null safety, and it does deliver. So if you consider this particular example, maybe a bit convoluted, I made it convoluted on purpose. I've got an optional, or null value on an ID, and I want to, return this ID, and if I don't check for when the ID is null, the compiler is going to warn me, an error out on me, and telling me that, I have to type guard against the null case because I cannot assign it straight to string. Great. So I do so on the next line, and everything nicely compiles and the code is nice and solid. And it's obviously a big improvement over Java, as we've seen, where pretty much anything can be null, you're on your own. And this feature is so great that you end up relying on it, and that is until it doesn't work. So in this particular case, if you just look at the last example from here and this example from here, the only difference that we see is really we just flipped the way we perform the check up top. So we check for the ID is different to null first, and then for the value of type foo. And sadly, the TypeScript gets confused in this particular case. So it's quite a common occurrence in my experience with TypeScript, where you end up tweaking the code so that it's semantically exactly the same. It just has to be written slightly differently in order to make it work. Like in this particular case, I mean, AND operator is commutative, especially in this simple case when there's no evaluation. Unions and pattern matching. Pattern matching because OCaml and Reason have got proper pattern matching. But TypeScript gets really close, and it's another one of the super cool features in TypeScript. Unions, by the way, or variants, for those who are unaware, allow you to express a concept of type or another type. And they're a mega powerful feature, especially combined with what you will see here, and the TypeScript feature to enforce the exhaustiveness of your checks. So I've defined the union up top for bar. They happen to be strings. And if I check in my function that takes only a union for just the value of foo, it's going to give me an error that, in other case, I'm going to have a fall true and return undefined. Therefore, I've not exhaustively checked for all of the cases. It's a mega useful feature. It allows you to write code which covers pretty much all of the cases. So at the bottom, I've addressed that. Everything compiles, I don't need the default case, and everything works beautifully. And at my company, we actually quite really like this feature, so we decided to flip it on its head and get closer to pattern matching by starting using the following pattern, where you start using switch true instead of switch variable, and then you can just cram any complex if expression into your case part of the switch statement, and do something that is very akin to pattern matching. So, for example, something like that. It really helps with validation. It makes it really clear to read from top to bottom. And then I personally got so used to this particular style of writing switch statements that it was like muscle memory at some points. And it happens not to work with exhaustiveness checks against unions. So this is exactly the same example as the first example with the exhaustiveness checks, just written in a slightly different way. I'm switching true against the possible values that can evaluate to true, rather than switching a value against things that this value is equal to. And the exhaustiveness is not working anymore in this particular case. So this is very interesting, because if you're writing this code and if you're reading this code, what you might be tempted to do, instead of rewrite it to do switch value and do the normal exhaustiveness checks, you add a default case. And when you add a default case, effectively everything is exhaustive. This is one of the most interesting things, in my opinion. We quite often, get data from a server, especially as front-end developers. We chat to third-party APIs. You kind of cannot necessarily trust what's coming out from a third-party API. So the safety at this boundary in between, a third-party system and your own system is paramount, in my opinion. And to parse, server responses, if you are using the fetch API, or you can use JSON.parse directly, provided you don't want any other library, you can use that. And in TypeScript, it's not about actually, in this particular case, a feature or lack of features in TypeScript itself. It's more about how, the standard library in TypeScript is typed. It allows you to effectively claim that the response is of certain type without performing any checks. So I can get a crazy JSON and claim it's a Boolean. It's going to be just fine. So it can lead to interesting scenarios like this. If you just scan through this code, it looks fine, right? We've got a type doctor with a name and shift both strings. We've got a nice function which takes a doctor and renders some information about this doctor as a string. And then we do a simple JSON parse on the response that we supposedly got from the server, and then we render a doctor and we get something that doesn't look like what we intended. Very simple mistake to make, because JSON parse didn't force us to perform any type checking as we are parsing. A simple thing as the response being wrapped in an array can lead to situations like that in your application. So this leads me to my conclusion that TypeScript is incredibly capable and confident. When you press it, it struggles a little bit. So the last language I want to talk about is OCaml. It's got all-encompassing, it's not a type system theory term, type inference, meaning that it's not only your var local variable that it will infer. You could theoretically write your whole program without a single type annotation, and it's going to work. So in Java or TypeScript, certain operations can be unchecked. The OCaml itself won't compile at least unless it knows the type of each and every single expression in the whole program. So, a function that takes a Boolean and a list of other Booleans, and if all of the Booleans in the second lists are true, or if the first Boolean is true, then it's going to return you true. So not the most super straightforward thing you can write, but it requires absolutely zero type annotations. So for example, it knows what B is because it's been piped into fold left, which is an equivalent of reduce. And inside of the function that we are using for reducing, we use the AND operator. Therefore, it immediately figured out that B is a Boolean. Therefore, also C is a Boolean. And then we ordered with A and figured out that A is a Boolean as well. So it can infer all of the types for you. And this is, an example limited to one function. In certain edge cases, it will ask you for a type annotation, but 99.9% of the time, you just don't have to annotate. It knows it. And type inference, I want to stress that it's such a great feature because if the compiler knows the type and you don't have to annotate it, the scope for lying to the compiler is much smaller. Variants are quite similar to TypeScript unions. So again, this is a very similar vibe to what we did with TypeScript. We define a variant of foo and bar. The only difference is bar also happens to hold the value of a float. And if we switch in a non-exhaustive fashion, it's going to warn us about the fact that we've not handled a possible value. So nothing too different so far. And of course, we fix it by addressing all of the cases. One of the concepts in here, the differences in between the TypeScript, is that in TypeScript we've seen that there's this concept of type narrowing. You can have a variant like something or something else, and you can perform a guard against it and turn it into just something. In OCaml, with an asterisk here, you cannot do it. A variant, the type constructor of a variant, so foo or bar in this particular case, cannot live in isolation. And the only way to guard against this is to use pattern matching. And a side note here, because I know polymorphic variants are a little bit different than that, but regular variants cannot live in isolation from their parent variant, if you will. So therefore, the only way to get a value out of this is to pattern match. It's literally the only way to figure out which value of the variant we are holding. And OCaml, it's quite humble, I think, to provide one and only good one option, not brag about multiple different ways in which we could do it. So for example, in TypeScript, you could do it by switch, you could do it by if statements, you could use the following function, you could use a array.filter with a type guard to get exactly this particular result, namely give me a list of things that contains things that are nullable or optionals or maybes, however you want to call them, and turn me into a list which is just some. In OCaml, the nice thing is there's only one way to get the value out of this, namely the pattern matching. Another one is interesting. So in OCaml, everything is immutable by default, but mutability is really a useful tool, whether be it for performance or sometimes it's quite nice for expressiveness if you don't want to go all crazy functional and you want to write something using a while loop because it communicates your intention better. Mutability is a useful tool to have. In OCaml, what's nice is that mutable and immutable types are fundamentally incompatible with each other. So you'll never end up accidentally sneaking a mutable type into an immutable type, or even worse, the immutable type into a mutable type. You can achieve this by either using a mutable keyword when you're dealing with records, or reference type, like in this particular example. So I find this example quite good about how, even though it's simple, about how those type differs. So first error is obvious, like you cannot mutate by default immutable let binding. The second example is quite interesting as well, because even the syntax for declaring something immutable, namely the reference, is wildly different from declaring something immutable. So the reference types, by the way, the reference itself is immutable, but the value it holds is. And even the way you assign or you mutate the value that the reference type holds, even the syntax for that is different. So it's quite hard to even make a mistake. And then if you make a mistake, as you can see in the two bottom examples, the compiler is going to warn you against that. This is not the feature of the type system. This is a feature of OCaml. which is the last feature I'm going to talk about. By far the coolest thing. Even though when I heard about some hipster sweet.js sort of things back in the day, I was really struggling to understand why would you like to create your own version and syntax flavor of the language. But PPX is a feature which effectively allows you to do syntactic extensions to OCaml. So for example, JSX could be implemented as a PPX. Not sure whether the current implementation is. And one of the coolest things that allows you to do is you can have a string and you can type some stuff as a contents in this string, and you can drop the type system into the actual value of the string and type check against it. So I've got a few, like GIF examples stolen from the internet. This is an example of a GraphQL PPX in action. So all of this you see from the keyword GraphQL all the way down to the bottom, really in OCaml is a string. The difference is that we flagged it with GraphQL, which tells the compiler use the GraphQL PPX for it. So not only you're gonna get autocomplete like you expect from any normal editor when you're writing your own queries, you're gonna get type checking against your own schema. And you could theoretically do it for any query system, be it SQL, Elasticsearch, etc., etc. Another cool PPX that is out there is a CSS PPX, or PPX BS CSS, if you want to find it on GitHub. A little bit harder to configure, but still amazing. So it allows you to write effectively CSS inside of your OCaml/reason file, and you're going to get proper power of a type system inside of your CSS. So in this particular case, it's telling you, you cannot use a unit of degrees when dealing with margins. Just quite more powerful than dealing with linters. This is what I think of OCaml. Simply reliable and humble friend. Thank you.